Okay, today we're going to look at some special examples of dealing with circular motion where we deal with horizontal or what we consider vertical circles. So a horizontal circle, what we're talking about is where the motion is parallel to the ground. So that means gravity is affecting the object the same in every position. So a good example of this would be like a car going around a curve or something like that. So in terms of circular motion, we don't necessarily have to have a complete circle. We could be dealing with a partial circle, so like a corner of a car could be a quarter, like quarter of a circle or half a circle or whatever. It doesn't matter how much of the circle we're dealing with because we could actually imagine it being a full circle anyway, like a traffic circle in terms of a car. So let's suppose we have a car going around a circle, and the question is asking what is our net force acting on the car. So let's suppose we have our car in the middle of the circle. We know that our centripetal force is always pointed towards the center, but what happens is we're actually, when we deal with these calculations, it's a lot easier to deal with the reaction force. So we know with Newton's third law, every force has an equal and opposite reaction. So when you're driving your car, you're turning your car inwards to the circle, so the car's force is inwards, but you as the passenger, what you're feeling for a force is outwards. We actually feel an equal and opposite force going outwards, and we call that the centrifugal force. Okay, so centripetal is inwards, centrifugal is outwards. And for all of our calculations we're dealing with this, we're actually going to be dealing with that centrifugal because it'll actually make it easier to solve. The good news is the calculation is the exact same, so centrifugal equals centripetal. The only difference is our direction is outwards. So a car going around a curve, the people inside the car, you get pushed outwards. If you're on a gravel road and you go around the corner, the gravel rocks are going to get shot outwards. So the centrifugal will be outwards, and that's it. So let's do an example where the question is a car travels around a curve with radius 50 meters and the coefficient of friction between the tires and the road is 0.75. What is the maximum speed the car can travel without skidding off the road? Okay, so for this question then we have car going around the circle, so we know our radius is 50 and friction is what's holding us on the road. So in this case what we want to do then, our net force is our two forces. We've got centripetal going outwards, right? That's pushing us outward. And then we have friction holding us inwards. So as long as the car is staying on the road, those two forces are equal. So what you want to do is in your formula, you want to go mv squared over r for the centripetal and make that equal to friction, which is mu times the normal force. But remember, normal force, because our car is flat on the ground, it'll be the same as gravity. So we can just go mass times 9.81. So when we look at this question, we can see that when we go to simplify it, we can see that our masses actually cancel out. Because we have a mass of the car on both sides, we can actually cancel them out. So that's why in the question I didn't give you the mass of the car. So that means a little tiny light car going around a curve has the same chance of skidding off the road as a big huge semi. The masses don't make any difference because they cancel out in the formula. So to solve this for velocity then, you see we get v squared over r equals mu times gravity. So we can actually simplify that a little bit. It'll be mu times gravity times radius would equal v squared. So our velocity is going to be the square root of mu times gravity times radius. And so you can either rearrange the formula like I just did and solve it that way, or some people would rather just leave it as v squared over r equals mu g, plug in all the numbers and solve it mathematically. So whichever you prefer, let's do it using the formula since I already figured it out. So we'd have 0.75 times 9.81 times 50. Square root that answer, and we'll be done. So I'll just type it in here quick. So 0.75 times 9.81 times 50. Square root the answer. We get an answer of 19.2 if we round it off. Okay, so that means a radius of 50 with that kind of friction, a car should go no faster than 19.2. Because what would happen if it did? That means your centripetal outwards would increase, right? If your velocity gets bigger, your force will get bigger, and then the friction inwards will never change. So if your velocity is too big, your outward force will be bigger, and then the car would not stay on the curb. It would miss and slide off the road and hit the ditch or whatever. So if the question was, let's suppose the question was asking how fast could it go in kilometers per hour, remember just times it by 3.6. So in this case, 19.2 meters per second is 69 kilometers per hour. So that's why quite often on a highway, when you go around a curve or something, quite often they'll give you a yellow sign saying, recommended speed is 60 kilometers per hour or something like that. So they usually go a little bit less just to be safe in case it gets icy or whatever, but usually those are just recommended speeds to kind of safe for normal conditions. Okay, so that's it for a horizontal circle. So they all work sort of the same. The only other kind of different question you could get is maybe like a satellite or something going around the Earth where we'd have gravity equal to centripetal. But we're going to do those questions a little bit later on, so we'll leave that out for now. So let's look at a vertical circle. So a vertical circle would be something that's up and down compared to gravity. So you be like a loop-de-loop for a roller coaster, or if you spin something like a pail of water over your head, you spin it around and around, so try not to get the water to fall out, that kind of thing. So in this case, let's look at the forces again. So if our object is at the bottom, we have our gravity pulling that thing down, but we also have our centrifugal force going downwards as well. So that means at the bottom, our net force will be those two added together. So we'd have Fg plus Fc. Okay, now let's go to the top. So if we look at the top of the circle, we still have gravity going downwards, but this time our Fc is upwards. So that means our net force will be Fc minus Fg. We're going to assume the centripetal is bigger, otherwise the object would fall down. So in terms of like a roller coaster or whatever, the centripetal force has to be bigger than gravity, otherwise you would fall out of the seat. So that's basically the key idea with vertical forces. So when you're dealing with a question like this, you just got to make sure you're understanding whether we're dealing with the top or the bottom of the loop. We don't worry about anywhere along the sides. So because if it was on the side, that means we'd have vectors. We'd have gravity going down, centripetal going out, so we'd have to combine those as a vector to get our answer. And what we find out is, because at the bottom we're adding those two together, so that'll be your maximum amount of force. And at the top, because we're subtracting them, that'll be our minimum amount. So that means the sides then will be just somewhere in between. If you did our vectors and we calculated it, it would be in between those two. So usually for a question, if you're an engineer or something, you want to make sure you can cover the maximum amount, so that would be you'd only have to worry about the bottom. Or if you're trying to figure out what's the minimum speed to make the loop, we'd only worry about the top. So the sides we never worry about, it's only top or bottom that we ever deal with. Okay, so let's try an example. So let's try one that says, what is the maximum force acting on a $5,000 kilogram roller coaster going through a 5-meter radius loop at 15 meters per second. Okay, so So this question, so we've got a roller coaster going through a loop, and the question's asking what's the maximum force. So if you're the engineer, you want to make sure that your roller coaster can withstand that amount of force. So in this case, because we're dealing where the maximum force is, we're dealing with the bottom. So that means our net force is what we're looking for. We want to figure out what that maximum force is on the track. So we want our net force to be the centripetal plus gravity. Okay, so that means all we have to do is figure out mv squared over r and add that on to mg. So just do those two calculations. So mv squared over r, so we got 5,000 times 15 squared divided by 5, and then we're going to add on 5,000 times 9.81. So when we do each of those calculations, this one works out to 225,000, and our gravity turns out to be 49,050. So our net force then is, add those two together, we get 274,050, which we can, let's reduce that down to just 2 sig dig, so 2.7 times 10 to the 5 newtons. Okay, so at the bottom, that's where our maximum force is going to be acting on the roller coaster. So the track in this case would have to withstand 275,000 newtons of force, roughly, to be able to hold the roller coaster up. So let's suppose now, let's do it the next one. Let's find out what is the minimum force on the roller coaster. Okay, so in this case, if we're looking for the minimum, so now what we're dealing with is the top. So because, let's go back to the diagram, so the top of our track is where it's going to be the lightest, because we got gravity and centripetal working against each other. So that means our net force then will be the same two things being subtracted. So what we do is we want to subtract those two. So the minimum force, so our minimum force will be the top centripetal minus gravity, so it would be the exact same numbers that we just had, but we'd subtract them. So we'd have 225,000, and we'd subtract 4950. So in this case, our net force then is 175,950. Or if we round it off, it'd be 1.8 times 10 to the 5 newtons. Okay, so in this case, the bottom of the loop, the roller coaster would have the most force. The top of the loop, it would have the least force, so we just add or subtract. The other type of question you get with this would be, what is the minimum speed the roller coaster would have to go so that it just barely makes the loop? So in this case, our roller coaster was going at 15 meters per second, so obviously it made the loop because our centripetal force was really big. So the case situations where you want to figure out what's the minimum speed, where you could actually just make the loop, we do a similar question, except we're going to have it so that our net force is 0. So that means our FC would equal FG, right? Because if our net force is 0, so at the top we'd have FC minus FG, but if that's equal to 0, we can rearrange the formulas to be equal to each other. So if our net force is 0, we can just solve these two things to be equal to each other. So we'd have mv squared over r equals mg. And once again, you can see that the masses don't matter. So in order to make the loop, the mass doesn't matter. We just get v squared equals g times r. So our velocity is just square root of g times r. So for a question like this, it's a pretty simple calculation. You just go 9.81 times the radius was 5. Square root that answer. Okay. So we got an answer of 7 meters per second would be the minimum velocity. So that roller coaster going 7 would just make the loop without falling. So obviously this question where it was going 15 or 12 or whatever, it was going way faster than it needs to. And that's it.